All right, hey everybody. So in this video, I want to define what it means for a matrix, and then we'll extend this to also a function being self-adjoint. So what does it mean for a matrix to be self-adjoint, and then what does it mean for a function, or more classically, we'll call it an operator, to be self-adjoint as well. Well, first I want to talk about a matrix. So a square matrix, an n by n matrix, is self-adjoint if, whenever you are given two n-dimensional vectors, v and w, your matrix satisfies the equation where you take the matrix m times v and dotted with w, that is equal to v dotted with mw. Right? So your matrix is called self-adjoint if this equation holds true for any two vectors v and w. Just in case you're wondering whether or not such functions or such matrices actually exist, I'll give you two examples right off the bat. The identity matrix 1, 0, 0, 1 is self-adjoint, and we can see that pretty quickly because the identity matrix times v is just v, the identity matrix times w is just w, and so both sides of this equation are just v dot w. Less immediate is this one here. The matrix 1, 0, 0, negative 1 is also self-adjoint, and I'll leave that to you to check. But so we've got this idea of a self-adjoint matrix satisfying this sort of interesting, it's almost like symmetry, but there's almost symmetry happening here. All right, now, this idea extends to the realm of functions or operators as well. So a self-adjoint operator, right, is going to be a function from Rn to Rn, and so this function is self-adjoint if it satisfies the following function equality, right? And you'll see this looks very similar to the matrix equality. Specifically, if I take any two vectors, v and w, then we should have f of v dotted with w equals v dotted with f of w. And just to confirm, v and w are n-dimensional vectors. Since f is a function from Rn to Rn, f of v should still give us an n-dimensional vector, f of w should give us an n-dimensional vector, and so this is the n-dimensional dot product. We're simply saying that a function is self-adjoint if these equations hold true. Okay, so the reason that I want to introduce this now is because it turns out, and we will prove as a theorem, that our differential of our Gauss map is itself a self-adjoint operator. Now, I say that, but we need a few caveats, right, which I've written here in orange. So this differential map is a self-adjoint operator, but we are supposed to think of self-adjoint operators as mapping Rn to Rn, right? This should be a function from Rn to Rn. So first, I'm going to be recognizing this as a function on tangent spaces, right? So the original differential operator was from TPS to T sub n of p of S2, but from our previous video, I can identify T sub n of p of S2 with just TPS. So I'm just considering this as mapping this tangent plane to itself, right? And because the tangent plane is itself a plane, it can be thought of as a copy of R2 sitting inside of three-dimensional space. So this is akin to a map from R2 to R2. Now, that being said, when we talk about the self-adjoint operator, one of the important things that we saw was that the dot product was part of the definition. Right? If I go back a slide, this was f of v dotted with w equals v dotted with f of w. And so we are looking at a dot product. Here we are looking at the vectors inside of this tangent plane. And so the dot product in this tangent plane is just the first fundamental form, right? Which was how we measured two, or we could take the first fundamental form of two vectors in the tangent plane by taking their R3 dot product. So this is self-adjoint with respect to the first fundamental form, and as we consider these vectors to both live inside of the same tangent plane, so the same first fundamental form can be applied to both of them. All right, so with those caveats, let's prove this theorem, and we actually have to prove a lemma first, right? So the lemma that we're going to use is that for any two, or I should say for any parameterization x, right, with its corresponding tangent vectors x sub u, x sub v, and then its corresponding normal vector, capital N, we have that n sub I dotted with x sub j is equal to n sub j dotted with x sub I, where here I and j are standing in for either our usual coordinate partial derivatives, u or v, right? So in other words, we could say, for example, that n sub u dotted with x sub v would equal n sub v dotted with x sub u, or any one of the other 4 combinations, filling in for I and j. So we want to prove this lemma, which we can then use to go on and prove the theorem. So what is the proof of this lemma? Okay, well, the key observation is going to be that for our parameterization, this expression, n dotted with x sub I, is equal to 0, right? The reason for this is that given any parameterization x sub I, right? Remember, this is a stand-in for u or for v. X sub u and x sub v both lie tangent to our surface. N is a normal vector. It's normal to the surface, and so the dot product of those two things should definitely be 0. What we can do then is we can take this equation as a starting point and take the derivative of both sides of this equation. So let me take the derivative with respect to j. And maybe actually let me, right, to be precise, this is a partial derivative. So this is the partial derivative with respect to j, partial derivative with respect to j, right? And again, j is just a stand-in for either u or v. It could be either. And it's possible I and j are the same. It's possible they're different. But what that gives us, right, is on the right-hand side, I'm just going to get 0 again, right? So I'm going to get all of this equals 0. On the left-hand side, I am going to need to use the product rule. So I have the product, right, the dot product of these two things. So our dot product rule said that this side became n sub j dotted with x sub I. So that's the derivative of the first times the second, plus the derivative of the, well, just the first by itself, let's say. So that's just n dotted with the derivative of the second. So that's going to be x sub I j, right? And so we have n sub j dotted with x sub I plus n dotted with xij equals 0. And so therefore, right, I can move one of these terms over to the other side. And what I'm going to get is probably easier to just rewrite it, but what I'm going to get is that all of this, the fancy technology, we're going to get that n sub j dotted with x sub I is equal to negative n dotted with xij. Awesome. Okay, so the reason why we might want to do this, or why we care about this, is because we know if our function is at least C2, if our parameterization is at least C2, then the order in which I take these partial derivatives doesn't matter. This is one of our big calculus 3 or our big multivariable calculus results, is that if I take the derivative of my function first with respect to I and then with respect to j, it's the same thing as taking the derivative first with respect to j and then with respect to I. So the order doesn't matter. So armed with that fact, right, this expression on the right-hand side is just negative n dotted with x sub ji. I can change the order of integration. And for the exact same reason that these two things are equal, I can say that this expression is equal to negative n sub I dotted with x sub j. All right, so for the exact same reason that these two are equal to each other, right, taking the dot product or the derivative of an expression that looks like this, the reason that these two are equal to each other is the same reason that these two are equal to each other. And so by transitivity, nj dot xi equals, whoops, I'm sorry, I should have this negative sign should not be here, for the same reason that this positive equaled this negative should equal this positive. So let me try that again. By transitivity, nj dot xi should equal positive ni dot xj, exactly what we were trying to prove up here in the lemma. Now, that sort of nice equality will end up being important in proving the theorem, right? And so here's the theorem that we were trying to prove. As a reminder, we were trying to show that this differential, was self-adjoint, which really meant that if I took the dot product, or in this case, the first fundamental form version of the dot product, right? And if I took the dot product of the differential applied to a vector v with a vector w, let me say that again, if I took the differential of a vector v and dotted it with w, that should be the same as if I take the differential of my vector w and dot it with v. All right, so we want to show that these two things are the same. But if we unpack this, right, we have the differential of our vector v, right, and we have our vector w. I can rewrite each of these vectors in the notation of, or as a linear combination of, x sub u and x sub v. Right, so my vector v could just be thought of as v1 x sub u plus v2 x sub v. Similarly, w, vector w, could be thought of as w1 xu plus w2 xv. Right, so my v1, v2, w1, and w2 are just coefficients, and I'm rewriting these vectors v and w as a linear combination of my basis vectors x sub u and x sub v. So I get this line over here is just equal to this line. But when I go to apply my differential, right, I really only know this one thing about the differential. I know that if I apply it to x sub u, I get n sub u. This was our big fact from the end of that video, right? The differential applied to x sub u will equal n sub u. Furthermore, right, not something that we explicitly showed on these videos, but worth noting, is that the differential is a linear function, which means that I can apply the differential to this linear combination of xu's and xv's, and I can break it up linearly. So what I get is that this differential is just going to be v1 nu plus v2 nv, and then the right-hand side hasn't changed at all. So at this point, right, I can actually take out the language of the first fundamental form, and this is just my R3 dot product, which I can write really nicely and succinctly as this line right here, right? When I go and I compute the dot product, I'll end up with 4 terms, right? This term, this term, this term, and this term. And those 4 terms can get written nice and compactly in this notation here. Now, according to the lemma that we just proved, right? According to the lemma that we just proved, we have this piece here. Let me see, this piece here, the ni dotted with xj, that is exactly equal to nj dotted with xi. So according to our lemma, this line is just equal to this line. And then we can go and start unpacking this, right? So at this point, we can unpack this addition back into a dot product. Notice, though, that my n's have gotten moved over to the w term. My x's are over here on the v term. And then this can be rewritten as v dotted with the differential of w. All right, and I should have colored this. This piece right here is exactly the piece that we were originally trying to show was equal to this piece. So we have indeed shown that this differential is self-adjoint. Now, not like a fact, right? Not even really a hard and fast rule, but something that happens regularly enough that I think it's worth mentioning is that if you have a self-adjoint operator, such as this, right, then you know that anytime you plug in d sub np of v dotted with w, you would get v dotted with dnp of w. Anytime you have such a self-adjoint operator, it's often worth it to try to see what happens if you take the expression, right? So this is the first fundamental form of a vector d sub np of v dotted with itself, right? So you have this self-adjoint operator. You know that the sort of v and w, there's this interesting symmetry in which the differential can be moved from one to the other. It's often interesting to see what happens if you take that self-adjoint operator and apply it to the same vector twice. And the result is going to be an expression that will be important to us going forward called the second fundamental form. So More on that in a little bit.